Hello and welcome back. My name is Bradley Cecil. This is the second video in our series, SerDes Basics. In the previous video, we focused on why SerDes exists. We saw that while parallel interfaces are simple and intuitive, they don't scale well as data rates increase. Issues like pin count, skew, and power eventually make it impossible to keep increasing bandwidth by simply adding more traces. So instead, we move to SerDes, where we trade many slow parallel signals for a smaller number of very fast serial links. But that raises a natural question: what actually happens inside a SerDes system? In this video, we're going to answer that question by breaking down the anatomy of a SerDes link. We'll follow the signal as it moves from one side to the other, and along the way, we'll introduce the key building blocks that make high-speed communication possible. At a high level, every SerDes link can be divided into three major parts: the transmitter, or TX, the channel, and the receiver, or RX. You can think of this as a journey. A bit starts as digital data inside a system, gets transformed and transmitted, travels through a physical medium, and is eventually reconstructed on the other side. Let's start at the transmitter. Inside most digital systems, data is processed and stored in parallel form. That might be 8 bits, 16 bits, 32 bits, or more, all moving together at relatively low clock speeds. The job of the transmitter is to convert this parallel data into a high-speed serial stream and launch it onto the physical channel. The first major building block in the transmitter is the serializer. The serializer takes a parallel data word and converts it into a sequence of bits. Conceptually, you can think of it like a shift register. Each clock cycle, one bit is shifted out onto the serial line. But because the output data rate is very high, the serializer must operate at a much higher clock frequency than the original parallel logic. This leads to another critical component: the transmit clock. Modern SerDes transmitters typically use a phase-locked loop, or PLL, to generate this high-speed clock from a lower frequency reference. The PLL ensures that the transmitted bits are launched with precise timing, which is critical for the receiver to recover the data later. Once the data has been serialized, it still needs to be converted into an electrical signal that can travel through the channel. This is handled by the transmitter driver. The driver is an analog block that takes the digital bit stream and produces voltage or current waveforms on the physical trace. In most high-speed systems, this driver is carefully designed to control signal amplitude, edge rate, and impedance matching. In many cases, the transmitter also includes some form of preconditioning of the signal. For example, it may apply pre-emphasis or feed-forward equalization to boost certain frequency components before sending the signal into the channel. We'll go into much more detail on that in a later video, but the key idea is that the transmitter can shape the signal to improve performance over a lossy channel. So from a physical architecture perspective, a transmitter typically includes a parallel data interface, a serializer, often implemented as a shift register or multiplexer tree, a high-speed clock generation block, usually a PLL, a driver that converts digital bits into analog signals, and optional equalization or pre-emphasis stages. All of these elements work together to take clean digital data and convert it into a high-speed electrical waveform that can propagate through the channel. The channel is the physical medium that connects the transmitter to the receiver. This could be a PCB trace, a connector, a backplane, or a cable. At first glance, you might think of the channel as just a wire. But at high data rates, the channel behaves less like a simple wire and more like a complex analog filter. Channel behavior has a very large effect on signal quality. Designing a proper channel is critical in high-speed design. To understand this, it's helpful to think about the channel in the frequency domain. When we transmit digital data, we are not just sending ones and zeros. We are sending waveforms that contain a range of frequency components. Fast edges require high frequency content, while slower transitions correspond to lower frequencies. The channel attenuates different frequencies by different amounts. In general, high frequency components are attenuated more than low frequency components. This is due to effects like skin effect, dielectric loss, and conductor roughness. As frequency increases, losses increase, and the signal loses its high frequency content. From a frequency domain perspective, the channel behaves like a low-pass filter. If you were to plot the channel's response, you would see that as frequency increases, the magnitude of the signal decreases. This attenuation directly impacts the shape of the signal in the time domain. What does that mean for our data? It means that sharp edges become rounded, transitions between bits become slower, and most importantly, energy from one bit begins to spill into neighboring bits. This phenomenon is called intersymbol interference, or ISI, and it is one of the central challenges of high-speed communication. In addition to frequency-dependent loss, the channel also introduces reflections due to impedance discontinuities, crosstalk from neighboring traces, and noise from external sources. So the signal that reaches the receiver is not the clean digital waveform that left the transmitter. It is a distorted, attenuated, and noisy version of that waveform. Now we arrive at the receiver. The receiver's job is arguably the most difficult in the entire system. It has to take the distorted signal coming out of the channel and reconstruct the original data as accurately as possible. From a physical architecture perspective, the receiver is a mix of analog and digital blocks working together. The first element in the receiver is typically some form of front-end conditioning. This might include amplification and continuous time linear equalization, or CTLE. The goal here is to partially restore the lost high-frequency content by boosting higher frequencies relative to lower ones. Essentially, it attempts to compensate for the low-pass behavior of the channel. Equalization in the receiver is used to reduce distortion from the channel and prepare the signal for accurate sampling. After this initial conditioning, the signal is passed to a sampling stage. But in order to sample the signal correctly, the receiver needs to know exactly when to sample. At these speeds, even a small timing error can lead to incorrect decisions. This is where clock and data recovery, or CDR, comes into play. Instead of having a separate clock signal, the receiver extracts timing information directly from the incoming data stream. It looks for transitions in the signal and uses those transitions to adjust its internal clock so that it stays aligned with the center of each bit period. Once the receiver has both the signal and the timing, it can begin making decisions. This is typically done using a slicer or comparator that determines whether the signal at a given sampling instant corresponds to a logical one or zero. In many receivers, additional equalization techniques are applied after sampling. For example, a decision feedback equalizer, or DFE, uses previous bit decisions to cancel out ISI from earlier bits. Finally, once the receiver has reconstructed the serial bit stream, it performs deserialization. The deserializer groups incoming bits back into parallel words so that the rest of the digital system can process them. So in summary, the receiver architecture typically includes analog front-end amplification and filtering, equalization such as CTLE and DFE, clock and data recovery, sampling and decision circuits, and deserialization logic. All of these blocks work together to take a degraded analog signal and turn it back into clean digital data. Let's step back and look at the entire system. A block of parallel data enters the transmitter. The serializer converts it into a high-speed bit stream, and the driver launches that signal onto the channel. As the signal propagates through the channel, it is filtered in the frequency domain. High-frequency components are attenuated, edges become slower, and intersymbol interference begins to distort the waveform. By the time the signal reaches the receiver, it is no longer ideal. The receiver then uses equalization to partially undo the channel's effects, recovers the timing using CDR, samples the signal, and reconstructs the original data through deserialization. This process happens billions of times per second, and when everything works correctly, the system delivers reliable communication even though the underlying signal is far from perfect. In this video, we've looked at the overall structure of a SerDes link and how data moves from the transmitter through the channel and into the receiver. We saw how the transmitter converts parallel data into a high-speed serial stream, how the channel behaves as a frequency-dependent system that distorts that signal, and how the receiver works to recover both the data and the timing from that imperfect waveform. In the next video, we're going to dive deeper into the fundamentals of how these signals behave. We'll look at how timing is generated and recovered in high-speed systems, and how techniques like clocking and synchronization ensure that data is sampled at the right moment. We'll also introduce differential signaling, which is a key technique used in SerDes links to improve noise immunity and signal integrity.